Hello and welcome to this talk about the effect of implant processing and current spread on vocal tract length perception. So in speech on speech and in speech in noise, listeners make use of voice characteristics to separate voices from one another. And the two most important voice characteristics are the F0 or the glottal pulse rate or the perceived pitch of the sound and VTL. And I'll quickly let you hear what the differences are. So this is a female voice. And if you change the F0s or you lower the pitch, then you get something like this. However, if you don't change the F0 or the pitch, but you change the VTL, you get something like this. And then what you're doing is you're not changing the pitch, but you're changing the perceived size of the speaker. So Fuller et al. Found that both these voice characteristics are also used for gender categorization. So if you use both, then you get a perceived male voice. Alright, and also found by Fuller is that CI users don't actually use this VTL information for gender categorization. So our question is why? So how is VTL then represented in speech? So on the left you can see the speech production system. You have the glottal folds together with the vocal cords that produce a source spectrum on the left. You can see the nice harmonics. And then the vocal tract, so indicated in blue, acts like a filter on top of the source spectrum with formant frequencies. These formant frequencies are influenced by, for example, the type of vowel that you are producing, so you're changing the shape of your vocal tract, but it's also influenced by the length of your vocal tract. So shorter people, their formant frequencies, they shift towards the higher frequencies, and taller people, their formant frequencies, they shift more towards the lower frequencies. So, and in the speech spectrum, you can see the formant frequencies are also represented there. Interestingly, for CI users, this is primarily thus a spectral cue in that sense. So it's primarily, vocal tract length is primarily spectrally represented in speech. So in a cochlear implant, spectral information is degraded. There are two primary ways in which this is done. So the first is the complex implant processing. So when a sound is recorded and there's a lot of processing going on before it is turned into these stimulation patterns. And then in the second step, the other degradatory step is the current spread. So a stimulation from an electrode before it reaches the auditory nerve, it is spread out through the endolymph. And this is also a spectral degradation. A temporal spectral degradation. And our aim thus is to find the relative contributions of both processes on VTL perception. So how do we get in the middle of these two processes? Well, what we can do is we can record from an actual cochlear implant. So we play a sound. The cochlear implant does a lot of processing and produces these stimulation patterns, which is then recorded by a device from Cochlear. And so we have a speech token, and this records for every electrode a stimulation pattern, which we can then translate into a temporal envelope. And this temporal envelope can be combined with filtered noise bands to create a vocoded speech. Alright, then how do we then get current spread? The effect of current spread, because we are not in cochlea, so we need to simulate that. And that we also can do through vocoding. So on the left you see vocoded speech. If you choose very sharp filters for your filtered noise, then very little information of one frequency band passes over into neighboring or other frequency bands. However, if you choose very broad slopes, such as in the 24 dB per octave for the current spread simulation, then a lot of information from one frequency band passes over into neighboring and other bands, and this simulates, or this is similar to what is happening in the cochlea. And then our final condition is vocoded, so that's just normal speech. So we want to find the VTL percepts of all these three conditions, and we do that through an experiment. So a participant is set in front of a loudspeaker, and three sounds are played, and one of these sounds has their VTL shifted through the World software, which is a successor of Straight. And we use DVTL, so differences in VTL of 0.5 up until 9, where in previous studies J&D, so just noticeable differences for normal hearing for VTL were about 1.7, and for cochlear implant users was about 7.2. So we have these three conditions. These are the results. For non-vocoded speech, we can see that it's very much different from the vocoded speech, and we see about a 1 semitone difference. However, for the two vocoded conditions, we actually don't see a difference, and this can be explained. So in Crew et al, we find that if you want to simulate current spread, 24 dB per octave is considered very mild current spread. If you want to, a medium amount of current spread, you would need about 12 dB per octave, and very aggressive would be 6 dB. So we did a follow-up study. We changed our filters, and you can see now that the J&Ds go up. So for medium amount of current spread, we chose 16.8. We get about 4.6 J&D, and for maximum current spread, even higher. So in conclusion, we measured the relative contributions of CI processing and current spread on VTL perception, and we found that CI processing, the effect is not that big, so it's about 1 semitone we found, and taking into account what kind of degradation is going on, that's not that much. So the effect of current spread, on the other hand, is bigger. How big is difficult to pinpoint because we don't know exactly how much current spread is actually happening in the cochlea. So a possible next step would be to make use of a new toolbox that was recently released, panoramic ECAP, and this supposedly measures the nerve response from a cochlear implant by a cochlear implant, and this would be very useful to see what the effect of current spread on VTL perception actually is, to also in the end get an idea of why it is that that this VTL is not used by cochlear implants for certain tasks. So that was my presentation. Thank you.